Thanks everyone for joining us here today. Radiant Vision Systems is a test and measurement equipment manufacturing company. We specialize in measuring light and color and providing automated visual inspection solutions across the entire globe. On today's agenda, we're going to start by giving an overview of light and color theory, beginning with the basics of what is light. Then we're going to walk through quantifying human visual perception and take a journey along the road, starting with the CIE tristimulus curves and arriving at the CIE color chart. Next, we're going to transition into talking about light and color measurement systems. So the equipment that is needed for the metrology of light and color measurements, getting into some of the benefits of CCD imaging technology. At the end, we're going to touch on some example applications where you can take light and color measurement into the lab and onto the production line. So starting off with light and color theory. So what is light? So light is electromagnetic radiation made of photons. And these photons we can describe by their energy or by their wavelength. So when we look at the entire spectrum of electromagnetic radiation, we have very energetic gamma rays all the way over to low energy microwaves and radio waves. Today, when we're talking about light, we're going to be focusing on a really narrow part of the electromagnetic spectrum called visible light. So visible light extends starting at the UV or ultraviolet and going up to the infrared or IR. So visible light is the tiny range of electromagnetic spectrum that our eyes respond to. So that's why we'll be focusing on this today during our webinar. So to start us off on our journey of light and color measurement, I'm going to introduce the concept of a spectral power distribution. So the plot that I have shown here is one that we're going to see throughout the presentation. So on our x-axis here, we have wavelength in nanometers, going from about 400 to 700 nanometers. Our y-axis is going to show relative power, and the gradient rainbow in the background is just shown for demonstration purposes. So the color in the background roughly corresponds to the color of that wavelength of light. So a spectral power distribution is one way to define the light output of a light source, and we're going to plot a few examples so you can get the hang of it. So first we have D65 or sunlight, which is very broad, illuminate A, LCD blue, LED red, and lastly, Heine laser. So when we're looking at these spectral power distributions, one thing you can notice that there's some power distributions that are very broad. So for sunlight, which is white, we have output at basically every wavelength in the visual spectrum. Whereas something like LED red is very narrow, so we're only getting output from wavelengths between about 600 and 670 with a peak around 620 nanometers. Even narrower than that is a Heine laser. So lasers have an output at a very narrow band of wavelengths. So this is a spectral power distribution, and this is one way to define the light output of something like a luminaire or a display. Humans, however, our eyes are sensitive instead to color and brightness. So we are not seeing or resolving spectral power distributions, we just see a resulting color and brightness. So the way that we do this is that the human eye has three types of cones, S, M, and L, and each of them is sensitive to a specific range of wavelengths. So as I was mentioning, the cones in our eyes, they can't detect individual wavelengths, rather they see the sum of the total light under that curve. So down here we have the kind of a rough spectral response of the three different cones in our eye. So again, the same plot where along the x-axis we have nanometers. So because humans don't resolve the spectral power distribution, one thing that can come about is that different spectral power distributions can actually look the same to our eyes. So a good example of that is white. So there's a few different ways to produce white. One of them is a really broad source like D65 or Illuminate A. You can also have a white LED. And one way to make a white LED is a white phosphor LED. So here we have a peak in blue and then kind of a gradual peak where the yellow phosphor is. So that could make one type of white LED. You could also have an LED that had red, green, and blue primaries that mixed together to make white. So when we're going along our journey to how do humans perceive light and color, one thing to keep in mind is what we really need is the resulting color and not necessarily the spectral power distribution. So quantifying human visual perception. So just to keep in context of why we care about this is that for most products produced, humans in some form or another are our target market. So if we're concerned about how bright something is and what color it is, ultimately the judge is going to be the human eye. So as you design and test your products, we need to match human visual perception. And to do that, we use the science of photometry. So photometry is the science of the measurement of light as perceived by the human eye. And this then keeps us to the visible spectrum only. And within the visible spectrum, the response is weighted by what's called the photopic curve, which we'll see in a couple slides. So adding to that is colorimetry. So that's the science of the measurement of color as perceived by the human eye. And kind of the next section of this webinar is going to do a deep dive into how the standards of colorimetry were derived and how they can be applied. So as we continue along to quantifying human visual perception of color, we need a mathematical language to talk about it with. So if you're a designer or an engineer and you need a part to be green, or you need it to be, a headlamp to be bright enough that someone can see it at night, you need a language and a standard that you can now communicate across teams and across industry to standardize. So what I'm going to be introducing is a mathematical language that quantifies brightness and color variation as perceived by a standard human observer. And additionally, so with light, we're going to talk about the human photopic response at each wavelength, so the overall response to brightness. And another level, which is defining actually the spatial emission of light. So first we're going to talk solely about the brightness and color, and then we're going to get into what we call the language of light, so luminance, illuminance, luminous intensity, as this is also an important part of photometry when setting up your measurement. Additionally is color. So we need to have a way to scientifically describe the human eye's response to each spectral power distribution that will give us the resulting color. And then we need a mathematical model to define those visible colors. And this is the CIE color chart. So we'll be working towards that in the next few slides. So here again, we have our trusty plot going from 390 to 700. And in the background, we have the spectral power distribution of sunlight overlaid with the spectral sensitivity of the human eye. So what this tells us is that the human eye is most sensitive to kind of green and yellow. And one thing that goes along with that is that that is close to the peak output of the sun. So our eyes are most sensitive where we receive the most radiation. Here the maximum luminous efficiency is about 555 nanometers. So this curve right here is called the photopic response. And again, basically what it means is if you have a light that's blue, you're going to be less sensitive to it than, let's say, a light that's green. So on this slide, we're showing the CIE tristimulus curves. So these are the mathematical way to determine the human perception of brightness and color. So when we look at this graph, again, we have our wavelength along the x-axis and relative power along the y-axis. And starting out, this plot right here in the middle, y-bar, this is the same as the photopic response. So when we use these three tristimulus curves, the y-bar is what we use to determine the brightness and overall response to the light, and then we add in the x-bar and z-bar, and together using these three curves, we're able to define the color. So over on the right here is the CIE color chart, so this is what we're going to be working towards. So first we need to discuss, how did we even get these curves? So these were determined kind of a few different ways, but one of the ways was using experimental setups. So one of the scientists involved, there were a few different ones, was James Maxwell, and he was doing color matching tests. So taking observers, so people that he knew, shining a white on, giving them a white target, and then giving them red, green, and blue lamps, and allowing them to adjust the output of those different lamps until it matched the white. So this is, a simplification, but from those experiments, it was determined these mathematical functions. So these were defined in the 1931 CIE body, which is a French body, so I won't try to pronounce what the acronym is. But from this, we get these curves. So again, just a little bit bigger here, we have X bar, Y bar, and Z bar, and this is the basis for the technology used in colorimetry. So what you do with these three curves is, for a light source, you take the spectral power distribution and multiply it by each of the spectral power distributions. Then from there, the integrals give you tristimulus x, y, and z. So these are now capitalized. When you see the lowercase x with a bar over it, that's describing the function. And once you've done the integral with the spectral power distribution, you get the tristimulus x, y, and z. So when you're doing colorimetry, kind of the first thing that you need to do is calculate your tristimulus x, y, and z. And to do that mathematically, you use integrals, and we're going to be talking in this presentation how you also do that with equipment, so with measurement devices. So once you have your tristimulus x, y, and z, you can combine them together to give you color coordinates. So down here we have the 1931 color coordinates. So our CX coordinate, and we'll introduce that on the next slide, is just a very simple combination of tristimulus x, y, and z. As we go to later, such as the 1976 CIE, we get the color coordinates U prime and V prime, and those are more complicated combinations. So we've added in some different coefficients to make the chart fairer in colors, and we'll show a little bit later a comparison between the 1931 and 1976 to show you the difference between those. So what I like to do now is show a couple examples of how we get from these tristimulus curves over to this CIE color chart. And I'm going to just give a brief intro on the CIE color chart in case you haven't seen it before. So earlier I mentioned that almost all the plots I was showing were going to have wavelength and then relative intensity. So the CIE color chart is not that. It has its own coordinate system. So along the x-axis here, we have the CX coordinate, and that goes between 0 and 1, or a little less than 1. And then the CY also goes between 0 and 1. And what it lets you do is by giving a coordinate, so let's say 0.2, 0.3, I can exactly define that color. So this chart isn't talking about the brightness of it. It's all standardized at normalized to 1 brightness, but it allows you to describe a color. So we're going to work through a couple examples. So as I said on the last slide, what we need in order to calculate Cx and Cy is our tristimulus curves, which we have, and now we need to know something about the light source. So in this case, what we want is the spectral power distribution. So I'm going to start with a blue LED. So just drawing in my spectral power distribution of a blue LED, and now you can see it calculating the capital X, capital Y, and capital Z. So my big X is going to be the area shaded under right here with red. My capital Y is going to be this little sliver right here, and Z is going to be this really big area here. So for this example, we're going to just use kind of some arrows to represent the relative size. So an arrow that points up is large, 2 arrows that point up is really large, an arrow pointing down is small, 2 arrows pointing down is really small. So I'll show an example with Cx. So our tristimulus X, which is the area bounded here, is small. Our Y is really small, and then on the denominator we get the really big component from Z. So our Cx coordinate is going to be small, because for blue we're dominated by the tristimulus Z on the denominator. Next we calculate Cy, so the same large denominator, but the difference here is that our Y component is even smaller, because see how we have much less area underneath the Y bar graph bounded by the spectral power distribution of the blue LED. So doing kind of our same little math here with small, we get our Cy is even smaller. So for blue, typically both Cx and Cy are really small because of the Z component on the denominator, and typically the Cx coordinate is larger than the Cy coordinate. So this shows us how for blue we get down here in this lower left corner of the CIE color chart. So continuing on with our example, next we look at a green LED. So again, the first thing we need to do is calculate our tristimulus X, Y, and Z, and then plug them into our formula for Cx. So here our X is small, we have our Y on the denominator, so this value is going to be small. And then for Cy, the area under here is larger, so our Cy is larger than our Cx, and that puts us up in green. And kind of depending on, if we were to shift this farther this way, we would come over here. But this is an example of a green LED. And then you're probably getting the hang of this at this point. So now we have our red LED. We calculate our Cx and Cy. So here our X is larger, our Y is big, our Z is really small. There's almost no Z component at all. So our Cx is large, our Cy, the same denominator, but we have a little bit less contribution from the green, is going to be medium. So in this case for red, our Cx is greater than our Cy. And just to round it out with white, so we have sunlight. And for this, basically all 3, capital X, capital Y, and capital Z, or tristimulus X, Y, and Z, are each about the same. So that leads us to our Cx and Cy are each about a third. So that puts us right in the middle of our CIE chart. So hopefully what you got from that is that the white point in the middle is where all the colors are mixed. And then when we find these 3 different corners, it just depends where the spectral power distribution is located. So that was kind of how you can take a light source. In this case, the information that we had about it was its spectral power distribution. And from there, we can calculate the color coordinates. So I just wanted to take a minute to talk a little bit more about the CIE color chart. So in this color chart, you can see we actually only have the X and Y coordinates. So the whole CIE color chart is actually three-dimensional, and this representation, so actually the Z would be coming out of the page at us. So this plot is showing a slice in 3 dimensions where we're on the plane that CX plus CY plus CZ equals 1. So this is a very common representation of color space, but it really just is one slice in a 3-dimensional color space. So the whole thing here, this is called the CIE color space, and this is every visible color to the human eye, defined by CX and CY coordinates. Along the outer edge here, we can see numbers like 380, 490, 520. Those are wavelengths. So as you get to the edge of the CIE color chart, that is where you would have like a pure wavelength. So earlier when we showed that Heaney laser, if we were to plot that, it would probably be down here along the edge. And then as you mix the colors together, you get closer to the middle. And in the middle, when all of them are equally balanced, that's when you get to the white point. Along here, this is called the kind of this curved line in the background. This is the Planckian locus, and this is where we're defining color temperature. So if you ever hear the term CCT or correlated color temperature, that's a way to define a white light source. So you can have light that's cooler, that's more blue, and it's actually represented in temperature in absolute scale in Kelvin, and this is a black body radiation curve. So you have cooler temperature and warmer temperature. One thing to note though with CCT, knowing the CCT isn't enough information to tell you the exact color. So everything along this line, for example, that's labeled with 10,000, every CIE color point that falls along this line is going to have the same correlated color temperature. So if you have CX and CY, you can get the CCT, but you can't go backwards. But in the lighting industry, it's kind of a common way to quickly tell someone, okay, is this a warm light or a cool light? And is also something that lighting consumers understand. So if you go to your local hardware store and you're looking at light bulbs, typically they're going to give you a color temperature in Kelvin. So that's along this line right here. And then you might have also noticed that we drew this triangle on here. So this is an example of a color gamut. There's all different shapes, but this is just an example one. And what a color gamut does is it shows you the producible colors using a device with those primaries can create. So let's say we have a phone screen, and if we turn it on full blue, we measure this coordinate, full green this coordinate, and full red this coordinate. What this tells us is any color within this triangle can be produced by mixing these coordinates. I can't, for example, though, make a color out here because it's not within the color gamut. There's no way to add, more red or more blue to this green and get farther up here. All I can do is pull it towards the blue or towards the red. So a typical thing to be defined for a device or product might be the color gamut that it has to produce. And the larger that the gamut gets, the more colors it can produce. So for certain industries, really expanding that color gamut is a priority of new device technology, as consumers really want, the most blue they can get and green they could get. And I also just wanted to share, I give this seminar live sometimes, and one question that I got one of the first times that I did it really stuck out to me, so I'd like to share it. So I was showing this on a projector and was mentioning, okay, this color gamut is describing basically what the projector could show, and someone raised their hand and said, well, on your projector, you're showing me up here this green. And that's a great question, because really it's important to keep in mind that this is a representation. So really there's probably no way for your computer screen, unless you have some really awesome new display that's not out on the market yet, to actually produce this green. So any time you see this chart, It's really kind of a representation to say this is green, but there's not really any way that especially printed sign or even something that you'd see on your monitor can ever really show you what this green looks like. But it's still important to kind of understand the coordinate system. So even though you can't point to someone and say, make it this green, you could tell them, make it, 0.2, 0.75. So they would know exactly what green you're talking about. Another way that the CIE color chart is used is to help define standards of how much a color can change. So it's great that we've gone through and showed, okay, this is how you define the color, but when you're making the product, there probably needs to be some range that the color can be. So McAdams ellipses are a way to define the just noticeable difference. So how far from a color, which is denoted by the dot in the middle of these ellipses, can you go before someone notices that the color has changed? And in this image, we've shown the ellipses at 10 times their actual size, so that you can actually see what's going on. What I want you to take away from this is just notice the difference in size between the green and the blue. So if you're a designer, right, and you have something that's green, you might actually have a larger tolerance of how much the green color can change, because you can have in this chart, you can have a larger variation in CY before, let's say, someone even notices that it's different. Whereas down in blue, if we're looking down here, maybe you can tolerate only a really, really small change in CXCY before the user notices. So this plot right here, this is the 1931 plot that had just the really simple formula, CX equals X over X plus Y plus Z. Over time, it's been updated and changed. So this example right here is the 1976 U prime and V prime. So what I want you to notice here is look how much smaller the green is. Look how much bigger the blue is. So part of the reason that this was done is to make the chart a little more fair. So now if you're talking about a change of 0.01 in CXCY, it actually has more meaning for it's changing that much, and we'd actually see this much noticeable difference. So whichever chart you use is really industry dependent. Some are really willing to go to the U prime and V prime. Others, for standard reasons, are using the 1931. But at its core, they're really the same thing because they have the same tristimulus X, Y, and Z values. And from there, it's just math to compute the coordinates. So if you're going to take anything away from this, just remember that when you're calculating color for colorimetry, the first thing that you need to do is calculate your tristimulus X, Y, and Z, and then from there you can figure out your color coordinates and plot them on the CIE color chart. So that wraps up our section on defining color. And as I mentioned, kind of everything that we have talked about here with color hasn't been brightness dependent. So we're not talking about how bright something is, we're just talking about the color. So of course, if we're going to talk about light and color measurement, we need to do the second half. So we started with color, and now we're going to take a step back and talk about the language of light. So when we're talking about the language of light, I'm going to be talking all about photopic units. So that means that the light is still, we're still measuring it following that photopic curve. So we're still filtering out some of the blue and some of the red, and we're most responsive at green. But we're going to instead be more talking about the geometry, you could say, about what we're measuring. So I'm going to work here from left to right, talking about each of these units. And to talk about it, I'm going to start by pretending that I'm designing, let's say, a luminaire, so a light bulb that's going in some kind of housing. So one of the first things I might care about is what is the total luminous flux, or lumen. So this is the total amount of light that's emitted by a light source, and we're integrating over the entire angular span. So this is something that you might do in, let's say, an integrating sphere, where you put your light bulb in an integrating sphere and it just adds up all the light in all the directions. The unit for that is lumens. and that's the photometric unit. The radiometric, so we have photometric, and then kind of the larger category that photometric is a subset of is radiometric. So that means basically not at all filtered by the human response. So the radiometric kind of equivalent of lumens is watts. So you might, again, if you go to the hardware store to find that light bulb, sometimes it might have lumens. It might also tell you the watts. So this is the luminous flux. So as we're on the journey of being a lighting designer, we now know the total amount of light coming out of our light bulb, but if we want to put it in a room, we probably need to know something about how that light is distributed. So do I have a spotlight, which is shining all the light just over a couple degrees, and it's going to put, one bright spot on my floor? Or do I have a more dispersive source? So it sends light in all of the directions. So this can be defined by the luminous intensity. So the luminous intensity is the amount of light emitted in the range of a three-dimensional angular span. So this is candela, and this is lumens per steradian, where steradian is a unit solid angle. So the luminous intensity of a device also is typically reported out as kind of a distribution. So you'd get a plot, typically in type C coordinates, that would show you where the light is going in all of the directions. Sometimes you just get kind of the max luminous intensity or luminous intensity in a direction, but it is common to see it as a distribution. So next we've defined our light source, the total amount of lumens. We've got our luminous intensity distribution. We know where the light's going in terms of candelas. And next we might care about the illuminance. So this is the lumens per meter squared, where the meter squared is basically a surface. So if we were designing that light for a hospital, one thing we might care about is if we put these lights on the ceiling, how much illuminance will there be on the table, and how much illuminance will there be on the floor? So both of those, especially in something like the medical field, are going to be highly regulated, because in order for surgeons to do their work, they need to have enough light. And then additionally, it would be, considered in anyone designing, let's say a museum or something. You need to make sure that you're illuminating all of your surfaces. So those first three, luminous flux, luminous intensity, and illuminance, all of those so far are just describing the light source itself. So nowhere in any of those was there an observer. These are just properties of the light source that you can define on its own. The next one, though, luminance, is the amount of light emitted from a light source or reflected back from a surface in a given direction. So this is the unit, luminance, that we most commonly think of when we're thinking of, okay, how bright is that laptop screen? How bright is that TV? We're going to do it in luminance, or candelas per meter squared. And in this little drawing, we have an observer here. So these are the four main pillars of the language of light. And you might have noticed that all of them are very similar in name. Lots of L's, very similar. As you start to work more, or maybe you're already doing it all the time, measuring light and color, one thing you'll find is that the term, for example, intensity, is used a lot when people mean luminance. So they might say, oh, what's the intensity of that display? When really they don't mean intensity, because intensity is from a point source telling you light in a direction. It's not really how bright is that display. So one thing I would recommend is if you're ever talking with someone and they want you to measure, and they're saying, what's the intensity, really try to understand the context of what they're measuring. So, do they care what an observer is seeing, or do they actually care about the light source on its own? So the language of light can be a little bit confusing, but it actually makes a lot of sense. And when you think about, is this, when I want this quantity, am I trying to describe a light source, or am I trying to describe a light source or something being viewed by a person? It can help you figure out which unit to measure. And speaking of measuring, the next section we're going to go into the types of devices that we can do to measure this. And actually here at Radiant, we're able to measure all of these different quantities. So if you're watching this and see something you want to measure, Even if we don't talk about it in this webinar, we can definitely talk to you more about how we can measure all of these different components of light. So yeah, let's finally get to light and color measurement systems. So as we set out from the start, the purpose of today's webinar is really human-centric measurement. So we want to know how humans are going to perceive brightness and color. And there's many different instruments on the market that can help you do this. So some of those include illuminance meters. You can kind of see a picture of one here, and those are meters that are typically handheld. If you ever go to a photo shoot, you might see a photographer kind of walking around and laying it around to say basically how much light is falling here. And then we're going to get into talking about luminance meters, spot colorimeters, spectroradiometers, and imaging colorimeters. So we're going to do a comparison, and first we're going to start with how these measure color. So we have along the top the difference between spot and imaging, which we'll get into next. And then along the side here, the idea of colorimeter versus spectroradiometer. So when we're doing colorimetry, what we're doing is we're using a filter-based system. And there's a slide that I'm going to show next that will go into a little bit more detail. But basically with colorimeters, we aren't the main difference here is comparing them to spectrometers. So when we have a spectrometer, one way to do this is to have a dispersive element that then has the light broken down into its separate wavelengths with a detector array. So with a spectrometer, we can actually measure that spectral power distribution. But as we've discussed earlier, we don't actually need the spectral power distribution. The spectral power distribution gives us more than enough information. So instead what we can do is, in order to calculate color, we need to get our capital X, capital Y, and capital Z, also called tristimulus X, Y, and Z. So basically, what is the total response through the X filter or the red filter, the green, and the blue? So previously, when I was using these filters, we were treating them as integrals. So we basically had the spectral power distribution, and we were integrating or shading under the curve light that passed through those filters. So in equipment, right, we're not sitting there and doing integrals, we actually use physical filters. So in a colorimeter system, you actually have filters such as glass absorptive filters that let light through according to these curves. So you start by actually pointing your colorimeter system at the device under test, so you have all of the light coming in. And then it takes 3 subsequent exposures. So first, all the light passes through the green filter, and we know now what our capital Y is. So what's the total amount of light that passes through this filter, aka this tristimulus curve. Then we rotate this filter wheel and take another exposure through the X filter. And now we know our capital X, how much light fits through that tristimulus curve. And lastly, we do the same with Z. So colorimeter systems, rather than measuring the spectral power distribution, which is information that we don't need all of that information, instead we can just figure out our tristimulus X, Y, and Z using a filter system. And again, we also have the photometric filter that we discussed, and then the three tristimulus filters. So that's the main difference between colorimeter and spectroradiometer. There's different types of colorimeters. The one that I showed was a moving filter wheel system. There are other ways to do it, but the 3 filter wheel system is the most accurate for colorimetry. And then the next comparison we have is spot versus imaging. So with spot systems, you're looking at just one point at a time. These are typically handheld. You hold them up and see a black dot, and then you take a measurement, and you're basically getting the average luminance and color of that dot. So you can have a spot spectroradiometer, so you're taking a spectrum measurement at one point, or you can actually get spot colorimeters. So these just do one spot at a time and use colorimetry, which is basically the filtering system for tristimulus values. This is compared to imaging colorimeter, where rather than taking a discrete point, you're able to image an entire scene using millions of pixels. So an imaging colorimeter, and this is what Radiant specializes in, uses a CCD. So a CCD is an array of photodetectors, and the CCD itself only measures amount of light, so nothing with color. We rely on the filter system to get the color values for us. So with this here, some of the advantages of using an imaging system, besides just time, of course, because rather than taking those 9 measurements, you can just take 1, and many times 9 wouldn't even be sufficient. But using an imaging system can help you contextualize your information. It also excels at measuring uniformity, so rather than just looking at 9 discrete points, it can find small changes in uniformity. Looking for defects such as pixels, blobs, and other small artifacts that's kind of shown over here. This is a false color image, kind of detecting some blobs. Another strength of imaging colorimeters is looking at LED arrays. So let's say you have an array of 200 LEDs and you need to quickly get the luminous intensity and color of all of those LEDs. You could go with a measurement system and go 1 by 1, or instead you can take a calibrated image of everything at once and get that data automatically. Included with that is rapid collection of multiple points and advanced analysis. So one example, and we'll get to more at the end of advanced analysis, is doing OLED correction. So for something like that, we need to be able to measure and register on every single pixel in the OLED display and measure those each pixel individually. So something that just is only practical with an imaging system. So when we're talking about CCDs, or charge coupled devices, one important characteristic is the resolution, and specifically spatial resolution. So the example here is showing if we measure an entire keyboard using 1 megapixel resolution versus 29 megapixel resolution. So we can just see that here we can see the pixelated, we can see it's very pixelated. We're only getting like 3 pixels across this bright point, whereas with 29 megapixel we can really see the detail and the distribution. And again, this is a false color image, so we're showing different luminance levels with different colors, purple being the darkest and green being brighter. So that's resolution. This is especially important for, especially when we're finding like small contrast variations. We want to get as many CCD pixels across it as possible. Finding pixel level defects and correction of displays. And having more CCD pixels is very important, especially as the device is being measured, get higher and higher in resolution. As you want more measurement pixels, you want more than 1-to-1. So you want as many measurement pixels as possible across one of your device pixels. And again, having higher resolution is great for detecting very, very subtle defects. So if you just see a small dip, you know, okay, is that just 1 CCD pixel? Or, you know, if you have 10 across it, you can really be sure that dip is there. So in addition to resolution, another really important characteristic of CCDs that might not be as obvious is the dynamic range. So at its core, dynamic range is the ratio between the maximum possible signal and the noise level in one measurement. And this is typically measured in decibels, which is log scale. And you want to calculate your signal to noise ratio. So on the right here, we just have kind of a couple little cartoons. But if we see, for example, if this green line was our measurement, we might be wondering, oh, is this a bright pixel? Like, is something happening here? But if our noise is really large, our signal might not actually, have that bump right there. So in order for us to know anything meaningful about this data, we can't have noise that's on the same order as our signal. So as I was mentioning, dynamic range is signal to noise. So the first thing that you want to do is try to minimize all of your noise. So to do that, you can cool the CCD. So kind of with all CCDs, you're going to have some kind of thermal electrons, so heat electrons that are coming in and looking like signal, but they aren't actually real signal from your device. So one way to reduce that is to cool the CCD. You can also do dark frame subtraction. So basically figuring out, okay, when I'm block my optical path so no light is getting in, but I'm still measuring some light, you know that you need to go through and subtract that pixel by pixel. So that was noise. So once we've done everything we can to get rid of noise, the next thing that we can do is boost signal. So the largest, the biggest impact we can have on signal is the well capacity. So the well capacity is basically how many electrons can fit into each CCD well. So one thing that comes into play here is something called shot noise. So this is basically a quantum effect where there's always some uncertainty in where the photon will go. So if you have a small well capacity shown here that let's say each only fits 5, if you have an electron that either doesn't show up or shows up where it shouldn't, 1 out of 5 is pretty significant. Whereas if you have a large well capacity that can fit maybe 100, 1 electron doesn't matter as much as it does when there's only 5. So because of the photon shot noise, the best thing you can do once you've taken the noise down as low as possible is, or the external factors of noise, is to increase the well capacity. And to do that is to physically make the pixels bigger. So that is important to keep in mind. So the reason that we bring this up too is that sometimes dynamic range and resolution kind of go head to head. So let's say you have a CCD that has pretty big pixels and you want higher resolution. Why don't you just take each of those pixels and cut it into 4? So that would increase your resolution, but then your well would be smaller, you'd have smaller pixels, so you'd get more noise. So really it's a trade-off between getting high resolution, but also making sure that your pixels are still large enough that you get the dynamic range that you need. So this is just a little illustrative slide kind of showing we have our original image, which is showing, so you can see on your screen there's these circles that are a little bit darker than the background. We add a small amount of noise, it's hard to see. And if we add even more, it gets almost impossible to distinguish. And additionally, if you have a noisy image, it really doesn't benefit you to have any higher resolution. So if you have noise, it's kind of effectively limiting your image resolution. So now tying all of this together into a measurement system. With an imaging colorimeter, you can have an electronically controlled lens on the front, and then precision tristimulus filters. So what these filters do, and I talked about it a little bit earlier, is we have the light coming into the lens going through, and then we have this filter wheel that rotates. So when you take an image, it actually exposes through each of these 4 filters. And it combines those together to create one image that can give you the CIE color for each individual pixel. Additionally, inside an imaging colorimeter, you can have neutral density filters. I like to think of these almost just sunglasses for the camera. So if you're measuring something that's really bright, you can put in front of it a filter that's neutral across wavelengths, but cuts the light down to only let through 10% of the light or 1% of the light. And then that's calibrated so that you get the actual result. And then in the back, scientific grade CCD, and what makes it scientific grade is having the large pixels. So we have the filters, the cooled CCD. So at Radiant, we cool and temperature stabilize our CCDs to be at 5 degrees Celsius to help remove noise, as well as performing dark frame calibrations. The scientific grade CCD going anywhere from 2 megapixels up to 29 megapixels. So with our last 10 minutes, I'm going to touch on some real-world applications. And one thing I'd like to say about this is almost every application that I'm going to be talking about has its own webinar. So as we only have 10 minutes to go into the applications, I want to just kind of give you an idea of what might be out there. And if you see something that's relevant to you, I encourage you to check out our other wonderful webinars, as well as reach out to us with any specific questions. So with that said, let's dive right into displays. So displays is kind of what Radiant is known for, one of our biggest strengths. And some of the common tests that we see are looking just for, differences in brightness and color. Again, non-uniformity, so is your display, a different color at the bottom versus the top. Looking for pixel and line defects. And again, most of these display tests can be done either at the backlight unit level, different component levels, once it's fully assembled. So there's going to be certain tests. So for example, like the sparkle test, sparkle is something that we see, it's a non-desired effect that comes about from anti-reflective coating. So the sparkle test would be something that you would do all the way at the end, whereas maybe something like a pixel or line defect test you might do really early in the backlight unit. So if you found, some pixel or line defects that couldn't be corrected, you could find it there before you go through and add all the other components. Light leakage, so, seeing kind of the LEDs along the edge. Mura, blemishes, image sticking, so does the image retain after you've switched it, and then view angle testing. So one thing that Radiant is definitely known for is our ability to do Mura measurements. So this is an image of the display that we've kind of showing some false color. So we've divided it into regions, and it's pointing out different areas and giving the just noticeable difference. So it can give quantifiable, repeatable data that can let you set pass-fails for, the size of a blob, the location of the blob, and all different parameters. Additionally, we can find defects such as dead pixels, particles on the actual outside of a display, or line defects. So here's just an example of it zoomed in, and we found that there was a cluster of dead pixels here. Radiant also, in the last couple years especially, has really been on the forefront of new technology and creating new measurement systems around that new technology. So today we focused a lot on measuring the light and color, but we also do a lot of exciting things with different lenses that we didn't touch on today. So one of them being for view angle, we have a conoscope lens. So our conoscope lens uses Fourier optics to basically look at one measurement point and then convert light from different angles into a plot. So this is an example of what you would get out of a conoscope measurement for doing view angle. So this is especially important in something like automotive, where you're going to be looking at the display at an angle. Next is OLED correction. So this is something really exciting that we've been involved in, where with LCD before, if you had variation from pixel to pixel, there wasn't really much you could do about it because you had a backlight unit and an LCD layer, and you couldn't really control an individual pixel. But with OLED and also micro LED, each pixel is its own emitter. So if you need one pixel to be brighter or a different color, you can go in and change the settings for that one pixel. So this allows increasing yield and just making a better product overall. So to do that, we've really been pushing the limits of our, what we can do with resolution to measure higher and higher resolution devices. Next, we have the ability to measure AR and VR headsets. So with these type of devices, standard lenses don't work, as the pupil is too far back in the lens that it cuts off the field of view. So we've developed our own lens that has the aperture at the front for measuring AR and VR headsets. We also do a lot with head-up display measurements, so measuring a virtual image. So here you don't actually look out and see a display, but if your eye is in the right position, you can actually see a projected image. And we can also have technology to measure the distance to that plane to meet the SAE standards. We also have tools for doing luminous intensity of near IR sensing devices for gesture control. And lastly, measurement of anti-glare layers, so sparkle. For backlit symbols, we have some new tools to make it easier to analyze an image that has many different areas of interest. So here, a dashboard, you could imagine if you had to take a spot meter and go point by point, that would be many hours of work. But with an imaging colorimeter, you can take one image and then using our automatic point of interest tool, you can very quickly output the luminance and color for every single point that you see in that image. And then lastly, kind of getting back to our roots with light and color measurement, you can pair an imaging colorimeter with a goniometer to create, here's a luminous intensity distribution plot. And you can also create IES files that can be put into third-party viewers for doing all your lighting design needs. So to summarize, imaging photometers and colorimeters have significant advantages for light and color and precise spatial measurements. By quantifying, human visual perception improvements can be driven to ensure that accuracy reflects the customer experience. So again, very human-centered and focusing on how human eyes perceive light and color. And then we can do multiple applications. And again, if you saw anything here that piqued your interest, I encourage you to check out the rest of our webinars that go deep dive into each of those on their own. So thank you.